is that one set of these weak spots is overlapping with the bright spot because the nitrogen atom is on the 1 by 1 spot. So you cannot really see. So the only way you can see it is to try to change the energy. You are hoping that they are slightly distorted, so you can see some spot going in and out. Okay, so that's the whole idea why they are changing energy to see the spot. So more detail, you can see more detail from the reference there. Okay, and just to be complete, there are other ways that you can measure lead pattern in addition to just pattern recognition. So far we just talked about pattern recognitions, just seeing spot pattern, or you can, nowadays you can actually measure the intensity of individual spot. But in the old, in the 80s or so, there's a new type of lead optic system, which called SPOT lead, which stands for spot profiling analysis lead. So instead of measuring a pattern, what they got is, so this is my lead pattern, let's say. I am going to follow one of the spots in real intensity, or I can follow the background between spots. Okay? And the hope is that you can quantify how the intensity change of one of the diffraction spots and compare with calculation, right? Assuming a certain absorption geometry that you have, and then deduce what is the real absorbing condition. And so this uses, I don't need to go into too much detail, it uses a very different type of electron optics called the hexapole, fancy word, double set of hexapole beam, it's sending the electron beam, bend it around, and then come back with a detector. And by changing the hexapole voltage, you can actually pick out one of these spots that you want, and then you can follow it. So this is typical image that you see. You can pick out spot like this, right? This is plotted in 2 dimensions. This is the intensity. This is the 0, 0 spot, and then you have the weaker spot, and you can plot it in different way. Okay. This type of optics is not very popular anymore because there's too much theory involved. So it's kind of don't like to do so much theory. So still, the diffraction type is the most popular because you can immediately recognize the relative position, if you like, of the overlay structure relative to the substrate structure. This really is for theorists who really want to do precise surface structure determination. Okay. So let me go quickly now to tell you a little bit more about, remind you, first of all, why is lead a surface sensitive technique? Very quickly, you remember the mean free path curve, right? The universal mean free path curve that we discussed about some lecture ago. Scattering, so really basically the mean free path between 50 to 500 volt in a solid is usually 2 to 3 monolayer or 6 angstrom. Each monolayer spacing is about 2.5 angstrom, right? Roughly 6 angstrom. So if you look at the universal mean free path, that's as low as you can get. You can't get any closer, you can't get any smaller mean free path. Okay? So typical interatomic spacing 2.5 angstrom. It means that the electron beam will suffer in elastic collision within 6 angstrom if you are using this kind of kinetic energy for the electron beam. So if you're looking at elastic scattering, right, meaning that you don't want changes in the kinetic energy of the scattered beam in the backward direction, then it has to be come from this 6 angstrom from your self-add region, right? Because other one will suffer in elastic collision, and then you don't have the same energy as you put in anymore. Okay, and you only see elastic scattered electron. Why? Because the probability, right? The probability of scattering picking up elastically scattered electron is much higher than inelastic one. So there's a technical jargon that people use. It's called scattering cross-section. Scattering cross-section, really, it's just a word physicists use to mean the probability of the electron getting scattered. That's what it is. So it's like a cross-section, looking cross-section. The bigger cross-section, it means that the probability of getting scattered is larger. That's all. And usually, given in some strange unit, historically, because it's due to nuclear physics, particle physics, they use megabarn. And megabarn is 10 to the minus 18 centimeters square. Okay, don't ask me why the origin, because in nuclear physics, the cross section is very small. So, but in electron scattering, cross section is quite large. So for elastic scattering, you usually have 10,000 megabarn, which would correspond really to about 1 angstrom square. So you can think of so classically you can think of within a 1 angstrom cross section. If you get your electron beam within that 1 angstrom cross section, you would get a scattering, right? If this cross section becomes smaller, let's say half an angstrom, you can see the probability of scattering off a half an angstrom dimension will be less, right? So that's the logic why we call it cross section. So for elastic scattering, it's 10,000 megabarn. For inelastic scattering, is about 1%, typically 1% to 0.01% of the elastic one. So you're getting 1 to 100 megabarn. So it's very, very small. So that's why most of the electron beam coming back are elastic ones. So the elastic signal will overwhelm your inelastic scattering cross-section. Okay. As such, the contribution from the lower layer will be less, because as you go penetrate the lower layer, you lost the electron beam and they don't come back because the cross-section is so small. Okay, so the most important one is the topmost layer. Now, in addition, you can change just to complicate things. You can measure the angular distribution of this electron beam, and you can measure. You can measure the kinetic energy of this scattering cross section, right? So let's say I have a electron beam. Let's say I have my electron gun is here. I send in my electron beam this way, hit my sample, right? And I have elastic scattering going into the solid, right? Some of them refracted elastically, so you can picture this going in. So you have some electrons going in, some electrons reflected back. They are all elastic scatter, right? And let's say now I have some magical way to measure the probability, how much electron scattering in as a function of angle from my service normal. So this is my service normal. I move my detector all around this direction. And what do I see? I will see something like this. So on one particular kinetic energy, I will see the forward direction will be very high, because you can imagine most of the electron will go in the forward direction. As I move away from the forward direction, the intensity is going to drop. So this is a polar plot of my intensity, of my electron scattering intensity. So I'm going to drop, and then at a certain point, this is my refracted beam. This is coming back from the electron. So in Lee, you are looking at the refracted beam here. Okay. And what I want to show is that there are little loop here. I don't want to call it. There's a lot of physics involved why this loop exists. I don't want to talk about the loop. It's interesting physics.